Last week's lecture dealt with naming, so let's see how you do. Naming of simple ionic compounds deals with naming the cation and then naming the anion. Traditionally, metals will usually form cations, non-metals will usually form anions. Additionally, the name of the anion is dependent on the type of anion that's present. So, we can usually tell an ionic compound based on the fact that it is a metal and a non-metal, or at least a metal and a non-metal. Though, if it's more than one non-metal, that usually suggests the polyatomic ion, charged groups of atoms that usually have a fixed structure. So, let's put it into practice. Let's take a look at this first one, K2SO4. We can see that this is a potassium, a K. And if we look on our periodic table, we can see the column it's in suggests the charge of potassium is going to be +1. And this SO4 tells us that these are special anions. These are polyatomic anions. And so SO4 is really SO4 minus 2. If we didn't know that, it was implied from the fact that there were two potassiums. So the correct name for this, the potassium ion, the SO4 minus 2 ion, is the sulfate ion, potassium sulfate. Most of the anions we deal with, most of the common ones at least, end in the ATE ending. Know the name, formula, and charge for the 8 common polyatomic 8 anions. One of which is the following: carbonate. So be able to go from the formula to the name, or in this case from the name to the formula. Lead 4, that 4 represents the charge on the lead, Pb plus 4. And carbonate, you should know, is a negative CO3 minus 2 anion. So these two would combine together to form PbCO3 2. It would require 2 carbonates to balance out the charge. A negative 2 charge would require another negative 2 charge. The only way to do that would be multiply it by 2 to take care of the plus 4. We can do a similar analysis for the rest of these. Hit pause and go through them real quick. No, really, hit pause. So, this should take you no more than 3 minutes to go through 1, 2, 3, 4, 5, 6, 7. Okay, I'll give you 4 minutes. Let's 30 seconds apiece. So, copper oxide, copper 1 oxide is a copper with a +1 charge. Oxide is O minus 2. So the balance formula would be Cu2O. Again, we can tell this oxygen is based on its common charge on the periodic table. This stranger one, OH is really an OH minus the hydroxide ion. There's 3 of them, each with a -1. That would represent that the iron is a +3. So the correct name would be iron 3 hydroxide. Now, acids are a little bit different. In an acid, rather than a metal, we replace the metal with an H+. And depending on the type of acid, it gets a different name. Anions derived from the element in its typical state, such as Cl-, these get the prefix and hydro and the ending ic. So this would be hydrochloric acid. So it gets the prefix hydro and the ending ic. Other acids like phosphoric acid in this case, the ic ending represents that it's derived from the 8 anion, from the ATE anion, the anion that ends in 8. Phosphoric acid would be derived from the phosphate anion, PO4 minus 3. And you would balance out the -3 charge with a bunch of H's, so the correct formula would be H3PO4. What about this anion? Again, we can tell it's a polyatomic. It's got some strange structures. So this is an SO3 anion. But if we look, it's not a sulfate. We already know what a sulfate is. So this is actually the SO3 minus 2 ion, or the sulfite ion. Yeah, acids derived from anions that have the ITE ending are called, get the OUS ending. This would be sulfurous acid. And these last two, sodium hypochlorite and AOCl, and zinc periodate. Normally with transition elements we have to indicate the charge. Zinc's kind of a special case. It's almost always +2. So we don't need to explicitly show it. So oftentimes it will be left out. Zinc periodate. Again, ideally it should take about 4 minutes, about 30 seconds per.